Welcome back. In this video, we look at our first machine learning algorithm, naive Bayes. Naive Bayes is considered to be a linear classifier. Linear classifiers take a linear combination of the inputs to calculate the output. Consider a data set with n examples. The x's represent the features, and the y's are the labels for a classification task. For each feature, x1 through xp for p features, a weight is learned from the training data. We also have an intercept b that's just used to fit the data. Since we often have so many features in machine learning, a matrix notation is more often used, where w here represents a vector of weights multiplied by the x data matrix. Then the single intercept b is added. Don't let the term linear make you visualize just a straight line. Think about y equals x squared. That's a line, but it's not a straight line. Naive Bayes is used for classification. The classification task can be a binary classification. For example, let's say we're dividing between spam and not spam. Or it can be a multi-class classification. For example, a sentiment analysis where the sentiment could be positive or negative or neutral. The naive Bayes algorithm takes its name from Bayes' theorem. Bayes' theorem is a way to calculate the probability of a label given the data. By taking the probability that we would see that data given the label times the probability of that label, all divided by the probability of the data. What we're trying to learn is the posterior. The probability of the data, given that we have a certain label, is called the likelihood. The probability of a label is the prior. And our denominator here is called the marginal, and it's actually just used to normalize the probability between 0 and 1. Let's make it a little more concrete with a spam example. The probability that a message is spam, given the data, which in our case will be the words, is going to be the probability that we see those words, given that it is a spam message, times the prior probability of spam messages. In other words, how common are spam messages, all normalized by the likelihood of the data. The probability will range between 0 and 1, so we usually choose a cutoff point like 0.5. Any probability above that would be classified as spam, anything below as not spam. Let's look at the chain rule of probability and how it applies to naive Bayes in text classification. The likelihood of a string of words 1 through D in a message would be the probability of the first word times the probability of the second word given the first word times the probability of the third word given the first two words, and so forth. This calculation would be difficult to implement, so a simplifying assumption is made that each of the predictors is independent. That's why it's called naive Bayes. It's a naive assumption, but it works out well in practice. The probability of each word is considered independently, given the label, and then all of those are multiplied together. The next few slides show how the parts of Bayes' theorem are calculated from the training data, and you'll see that it's basically just counting. Let's look at the prior first. The maximum likelihood estimate of a given class is just the count of that class divided by the total number of items in the training data. The estimated probability of a value I for class C is just the count of observations in the training data that have value I and that class divided by the total number of observations in that class. It's possible that some of these counts will be 0, making our probability 0, And since we're multiplying the probabilities, that would set the whole thing to 0. To prevent that, smoothing is generally used, where we add small amounts to the numerator and denominator to prevent zeros. We could have quantitative predictors. In that case, the mean and standard deviation of the predictor can be estimated, and we'd really like these values as they're associated with each class. Therefore, separate mean and standard deviation values are computed by class. A naive Bayes classifier with quantitative predictors is often called a Gaussian naive Bayes classifier. We'll look at an example of running a naive Bayes algorithm in a minute. And what we'll do there is we'll divide the total number of examples that we have. We'll divide it into a training set and a test set. We'll run the algorithm over the training set to build a model of the data. And then once we have that model, we can input new data that it's never seen before, this set-aside test set, to evaluate how well the model works. Some of our algorithms are going to have a lot of model parameters that we can tune. So in that case, we'll need to set aside a portion of the training data for validation to test out different values for these hyperparameters. We'll do that when we get to a neural network, but for now we'll just be dividing our data into training and test sets. Once we have our model, we can evaluate how well it does on the test data and compute metrics like accuracy, which is just the total number of correct predictions out of the total number of test set items. We often print out a confusion matrix here for a binary classification task. The true positives are items that were really of the positive class and classified that way. False positives are false but classified as true. The true negatives are items that are false and classified as false. And the false negatives are items that are true but classified as false. And what we want to see in the confusion matrix is on this diagonal here, we want to see most of the observations fall either here or there, because on the opposite diagonal, those are errors. So another way to look at accuracy is the true positives plus the true negatives over all 4 of those values. And sometimes people report an error rate, which is just 1 minus the accuracy. Other metrics that are sometimes used are recall and precision, where recall measures the true positive rate, and precision measures how accurate we were in guessing which ones were of the positive class. A Kappa score is used sometimes. A benefit of a Kappa is that it tries to adjust for the probability that you guess correctly by chance. In other words, if the classes are in balance, a classifier will tend to be skewed in that direction. A disadvantage of Kappa is that there's not universal agreement on what a good Kappa score is. Here is a guideline that's often referenced but seldom agreed upon. The general idea is that the closer you get to 1, though, the better it is. Another metric is an ROC curve. It's a visualization where we have the true positive rate on the y-axis and the false positive rate on the x-axis. So the more we go up towards this upper left corner, the better our classifier is. This name ROC stands for Receiver Operating Characteristics, and that reflects its origin in communications technology back in World War II, detecting between true signals and false alarms. The ROC curve visualizes this trade-off between predicting true positives while avoiding false positives. The related metric is AUC, area under the curve here. AUC ranges from 0.5, which would be a classifier with no predictive value, to 1, which would be a perfect classifier. Let's look at an example from the GitHub. We're using a spam data set from the UCI Machine Learning Repository, which is a great place to find some data to play with. It contains about 5,500 messages that are labeled either spam or ham. In other words, spam or not spam. So I'm going to use pandas to read that in, output the shape of it, and use head to show the first few rows. Here are the labels, binary 0 and 1, and here are the messages. We'll do a little bit of text pre-processing. I'm going to use nlp20 to help me. I'm going to do the TF-IDF vectorizer that we talked about in the previous video, and I'm going to use the stop words from nlp20. I'm going to let capital X represent the data, the text of the messages, and lowercase y be the labels. Then I can take a look at my data and a look at the labels. I need to divide into train and test, and I'm going to use the built-in method from sklearn to do that. Let me hit a return here so we can see the parameters. The first two parameters are just the data and the labels. I'm telling it I want 20% of the data to be in the test data, and I give it a random state. The benefit of that is that every time I run this notebook, it will do the same train test split. And I see my train shape here. I'm going to fit transform the vectorizer on the training data only, and then apply that to the test set. So let's take a peek at what the data looks like now. It looks like sparse matrices. Now I'm going to train the classifier. I'm going to import the multinomial naive Bayes classifier, and I'm going to use the default settings. And what we see here, that's an alpha of 1. If it were 0, that means we don't want smoothing. And the default is fit prior is true. I want it to learn the class priors from the training data. This line of code sets up variable naive Bayes to be an instance of this multinomial naive Bayes classifier. Once we do that, we can apply the fit method using our training x and y values. It's very simple syntax. This block of code, I'm just proving to myself that it did learn the prior probability of spam. Here I'm calculating it manually from the training data. It's about 13%. We can also extract it from the classifier, which we called naive Bayes. It comes out as the log, and by taking the log of what I calculated manually, we can see that they're the same. Taking a peek inside our model, we can see some other things that it learned. Basically, it learned log likelihoods of words given the class. sklearn is a little bit opaque. It doesn't really tell you too much about what it learned and why. So I'm just kind of showing a little bit of insight that you can extract from the model, although normally we don't do this. Let's evaluate on the test data. I'm importing the metrics from sklearn. First, I need to make predictions. Given our model, which we called naive Bayes, we can run the predict method using the test data. And what we'll get here is a vector of predictions. We can print the confusion matrix. We do see most of the observations on this diagonal. A few errors over here, a few false negatives. We didn't have any false positives. We can print a lot of those metrics that we talked about. Accuracy of 96%, a little better. Precision and recall. A nice feature of sklearn is this classification report, which gives us precision and recall by class. And over this column just tells us how many observations were used to calculate these statistics. We get an overall accuracy of 97% when it was rounded to 2 decimal places. And we have the macro average and the weighted average. Macro meaning we averaged these two numbers, and weighted meaning that we weighted them by the number of observations in that class. So we got a number that sounds pretty good, 97%. Is that really good? It's not bad. If we had just guessed not spam every time, we would have 87% accuracy. So that's a very simple baseline you can always check with. And so it seems that naive Bayes did learn something, since this is several points above this simple baseline. Here I'm showing some code where I'm getting the row numbers of the misclassifications. And that will enable me to loop through those and look at them and see why it might have not done a very good job here. And after looking at that, notice that a lot of these have all caps, a lot of these have numbers. So maybe we should pre-process the data a little differently and we might get better results. So I'm going to do a little manual pre-processing on the original data, going back to the original data frame that we read in, to replace any digits with this token num, likewise to replace any punctuation with this token punct, and all caps with this token caps. So that would make it easier, I'm hoping, for the classifier to identify when these things occur. And here I'm showing examples of what that now looks like. I'll go through the steps again. Train, test, split. I'm using the same random state. Do the vectorizing the same as before, and then the training. And we see our accuracy went up, but probably more importantly is that we see that our recall went up. It was in the 70s on the previous attempt. So a minimal amount of work here in pre-processing got us a little bit better results. I have one more try in this notebook. I'm going to try the binomial classifier instead of the multinomial classifier. Going through the same steps, instead of using counts, I'll use binary present absent. I'm using the Bernoulli naive Bayes, and seeing that it did do slightly better. I did a little analysis here after digging into the documentation to compare how the multinomial versus the binomial classifier work. And this is a little bit of speculation on my part, but I'm thinking that the Bernoulli might have done better because it's really the presence or absence of certain words in spam that was going to be a strong predictor. So in this notebook, we've run through a couple of examples of using the naive Bayes classifier. Naive Bayes is a simple and fast algorithm. It's a good choice for baseline results in machine learning. Naive Bayes will perform very well on small data sets, but generally you'll get greater accuracy if you have a lot of data using more sophisticated algorithms. But for small data sets, naive Bayes is actually hard to beat.